To understand how liquids and gases move, we don't need to start with scary equations. We start with a simple observation: nature has two ways of moving. Sometimes it's orderly, and sometimes it's chaotic. The first type is laminar flow. The word laminar comes from the Latin lamina, meaning thin plate or layer. Imagine a deck of playing cards sliding across a table. Each card moves smoothly over the one below it, never mixing, just gliding in parallel lines. In a pipe, this looks like a professional rowing team. Everyone's oars are in sync, moving in perfect, parallel lines with no bumping into each other. Then there is turbulent flow. This is highly disordered and messy. Instead of straight lines, the fluid zigzags and swirls. These swirls are called eddies. Think of a crowd leaving a stadium after a big game. People are pushing, turning, and moving at different speeds in every direction. Usually, thick fluids like honey moving slowly are laminar, while thin fluids like air moving fast are turbulent. Nature isn't always one or the other. Sometimes flow gets moody and switches back and forth. This is called transitional flow. How do we know which flow we'll get? We use a magic number called the Reynolds number, or think of it as a tug-of-war. On one side, we have inertia, the fluid's desire to keep moving fast. On the other side is viscosity, the fluid's stickiness or internal friction. Mathematically, we write it like this: ρ equals rho times v times d divided by mu. Rho is density, v is velocity, d is diameter, and mu is viscosity. In pipes, the rules are clear. If ρ is less than 2300, it's laminar. If it's greater than 4000, it's turbulent. Anything in between is the messy transition. Consider a canoe moving at 5 mph. Its Reynolds number is over 10 million. Because that number is so huge, the inertia bully wins easily, and the flow is definitely turbulent. If we cut a pipe in half, what does the speed look like at different spots? This is the velocity profile. In laminar flow, it's a perfect parabola. But in turbulent flow, those chaotic eddies mix everything together. This makes the velocity more even across the pipe. It looks like a blunt-nosed bullet. To calculate this, engineers use turbulent viscosity. Unlike regular viscosity, which is a property of the fluid, this is a property of the flow itself. When fluid touches a wall, it sticks. In turbulent flow, this boundary layer has its own anatomy: a tiny viscous sublayer, buffer layer, and the fully turbulent outer layer. When fluid first enters a pipe, it takes time to realize it's in a pipe. This distance is the entrance length. Why does this matter? Turbulent flow costs more power to pump, but it's great for mixing cream into coffee. Laminar flow is orderly but mixes poorly. In short, laminar flow is the beauty of order, and turbulent flow is the power of chaos.